the drawdown content of a region in R2. We'll just extend that to R1. Oh, okay, you already have it.
Yeah.
All right, we have this idea that if you have a region in R2, you want to compute the volume, then find a bounding box for that region. We'll only talk about volumes of bounded regions. Maybe you know that you can't talk about volumes in areas of unbounded regions. And one way to do that is just take some sort of a limit as the bounding box gets big. Take that bounding box, break it into bits. And then you can get two different volume estimates. One by counting up how many squares are completely contained in the region. And the other by counting up all of the squares that contained anything in the thing. And so you get an underestimate, you get an overestimate, and there's no reason you can't do this for Rn for any n. If you have a bounded subset x in Rn, then you can find some bounding rectangle, a1b1 plus a2b2 plus a3b3, and so on. Which contains x. So what does a bounding rectangle mean? That just means that x is a subset of R. If I take a bunch of different subdivisions, one of the first coordinate, one of the second coordinate, one of the third coordinate, and so on, then I can subdivide this bounding rectangle, bounding high-dimensional rectangle, up into a bunch of little high-dimensional rectangles. I'll call that a subdivision of that rectangle. So, if anyone needs them, I wasn't sure whether I actually handed these out last time, so I pushed out new ones if anyone wants a copy of the notes. Okay. Once you have a subdivision, you can find an inner volume by counting up all the n-dimensional volume in all of the n-dimensional rectangles completely contained in the figure, and another volume by counting everything that intersects the figure whatsoever. You can find an inner volume, the sum of all the inner rectangles, their volume. An outer volume, do the same thing, but with the outer rectangles, where the, in of x comma delta is a set of all elements of delta such that j is a subset of x. The outer rectangles are everything with j intersect x, not equal to the empty set. And of course, this is built into it, a definition of what the volume of a rectangle is, but you already know what the volume of a rectangle is. You should just take the product of all of the dimensions. Nice. And you can come up with other senses of what volume should mean by varying this formula. So one thing that you can cook up is, and this might even be like a decent thing to be a final project, you can compute what's called the Hausdorff dimension of a set. By varying a dimension an awful lot like this, putting a little alpha up there, and saying, well, that's like an n over alpha dimensional volume. And there will be a single choice of alpha for which it will be maybe not zero and maybe not infinity. That's the dimension. So, how many people have heard the statement that the Cantor set is like 1 over log 2 dimensional? That's one way of making sense of that statement. You can figure out for what variant of this sort of definition Cantor set has non-infinite, non-zero measurement. But that's not what we're going to do. That's something that you might do for like some sort of project. I can compute just volume by taking the supremum of all of the v minuses, or the infimum of all of the v pluses. If they're the same, we'll call x a figure, which is just one of many examples of a mathematical notation saying these are the only types of things that I'm going to study. Maybe figure is more meaningful than something which you see happen in some fields where they just call such objects good. We'll call them figures, but those are the objects which are good for us. And we set the volume to be either v plus or v minus since they're the same. Everything you know about volumes in R2 still happens. And I won't prove these at all, but maybe we'll see if you believe them. X is a figure if and only if for every epsilon bigger than 0, there exists a subdivision delta such that v minus of x comma delta is less than or equal to v plus of x comma delta less than or equal to v minus of x delta plus epsilon. That seems reasonable. And maybe you even believe, have an idea how the argument would go. Maybe we need some lemma about how any two subdivisions have a common refinement. That's true, because you know it's true for the interval from a to b. It's true for any subdivision of an interval. You know that, so now just push that up. And refining a subdivision gives you better bounds on d minus and d plus. And that's basically all you need to push through exactly the proof that we did in the case of dimension 2. That makes sense? Monotonicity. If x is a subset of y, then v minus of x is less than or equal to v minus of y, v plus of x is less than or equal to v plus of y. And well, if x and y are both figures, then you can always plus or minus. Am I recording? Good. If x and y are figures, then so are x intersect y and x union y. Moreover, the volume of the union is equal to the volume of x plus the volume of y minus the volume of the intersection. We proved something like that for the drawdown content, right? / you did it for homework? I think we did it in class.
I'm pretty sure we did it in class.
Yeah, there's something about how you draw both of the regions whose volumes you want to compute. You write down what the NO and outer Darboux sums for both sides of this equation are. You figure out what things are double counted, what things are undercounted, and go from there. And in fact, we proved something about v plus and v minus having some sort of inequality, and those inequalities together give equality. So what I think I want to do a little bit of, because I'll need it in the next bit, is let's soup up that proposition a little bit. What if I have lots of different regions? Yeah, these can be color-coded. x2, x3, x1. Then you can take the union of all of them and ask what the volume of that is. And you would say, oh, well, that should be like the sum of all of the individual unions as like a first estimate. So you'd say, well, that v of x1 should be like v of x1 union x2 union x3. That should be like v of x1 plus v of x2 plus v of x3. But that double counts some stuff, doesn't it? So now let's just take all the stuff that we double counted and uncount all of it. Fair enough. But I've uncounted too much. Because, right, so that region, x1 intersect x2, that got double counted, and then I subtracted it. That got double counted, so I subtracted it. That got double counted, so I subtracted it. But I think I've uncounted that region too many times. So So you need to add that back. And that's what this theorem is saying. It's just unpackaging what that result gives. Plus v of x1 union x intersect x2 intersect x3. It's just unpackaging that idea. And let's maybe think about the proof of it. I won't actually go through the proof because I mean the details of the proof I don't think are that important. We'll see the ideas in just going from n equals 2 up to n equals 3. So let's see what the proof even says. Well, maybe I'll point out this. You could try to take that side when you have like an infinite union of sets, and you could figure out what you should wind up with. Maybe you would think, well, there should be some like limit of the thing on the right. But the sense of measure we're using is not well behaved under big unions. You can take, say, an infinite union, countable infinite union of a bunch of points. And out of those points, you can get all the points in Q cross Q. But each one had no volume, and the union has positive volume. So infinite things don't behave well under this. If you want to do that, you have to do the Lebesgue measure. But let's actually go to the proof. So let's just write down what the proposition says when n equals 2. I think that'll also be a good way to unpackage what this notation even means. So when n equals 2, this says that the volume of x1 union x2 is, well, first let's plug in I equals 1. So it'll be negative 1 to the I plus 1. So negative 1 squared, that's plus 1. Of the sum, well, notice here, this is like I j's. There are I things in that list. So when I equals 1, it's just a sum from j equals 1 up to 2, I guess, of the volume of the intersection of all of those x's. You intersect a single thing, you just get that thing. So when j1 equals 1, you'll just get the volume of x1 plus the volume of x2. So there's the I equals 1 term when n equals 2. The I equals 2 term says, well, take negative 1 to the 2 plus 1, that's 3. Of the sum over all choices of j1 and j2, where 1 is less than or equal to j1, is strictly less than j2, is less than or equal to 2. So how many choices of j1 and j2 are there to do that? Just one? What's that choice?
1 and 2.
1 and 2, yeah. Of the volume of x1 intersect x2, is that exactly the proposition on the previous page that says what the volume of a union of two things is? I hope it is. So when n is equal to 2, this proposition is just saying the thing that we already know. Let's see how to, so instead of, well, that's volume of x1 plus volume x2 minus volume of x1 intersect x2. Let's see what the proposition says when n is equal to 3. So when n is equal to 3, first we add up the sums of all of the single sets, the volumes of the sets on n. Then we subtract all the intersections of 2, and then we add the intersection of all 3. So volume of x1 plus volume of x2 plus volume of x3 minus volume of x1 intersect x2 plus volume of x1 intersect x3 minus volume of x2 intersect x3 plus the volume of x1 intersect x2 intersect x3. So that I is just saying how many sets to intersect up. The inner sum is just saying, okay, go over all of the possible ways of intersecting that many sets. And I mean, I guess let's just expand that out. So that'll be volume of x1 plus the volume of x2 plus the volume of x3 minus the volume of x1 cap x2
Oh, that should be a plus, shouldn't it? Fair enough.
And let's figure out how to show that that is true, assuming the result when n equals 2. So I feel like I'm going to go through the inductive step, but only going from 2 to 3. Just to avoid notational nightmare. So let's try to prove this, that the volume of x1 union x2 union x3 is exactly that. So let's do it. So the volume of x1 union x2 union x3, I can group things together. So it's the volume of x1 union x2 union x3. Is that now a union of two things? Yeah. It was already, but. So we can apply proposition 3. See, that should be the volume of x1 union x2 plus the volume of x3 minus the volume of x1 union x2, parentheses, parentheses, intersect x3. Wait, do you see another union of two things in there? Do you see another union of two things in there? Well, but you almost do, right? As you see, up there is union of two things together with an intersection. Who remembers the distributive law for intersections and unions? Well, I mean, it says what you think it says. It says that intersection distributes over union and union distributes over intersection. So we could just appeal to proposition 3 immediately on this, but then we would still be left with this. So I only want to make one more appeal to prop 3. So that'll be volume of x1 union x2 plus the volume of x3 minus the volume of x1 intersect x3 union x2 intersect x3. Math reveal top 3? And maybe I'll even start color coding. So right here I see the volume of x1 union x2. Is prop 3 even the right thing to be citing? You guys are being really quiet, and sometimes that means that I'm just saying crazy things and no one's stopping me.
So after the two volumes of the two things that are intersecting. So I guess like you have a union there.
Yeah.
So you just do the volume of x1 intersect x3 and then the volume of x2 intersect x3.
Yeah, and then you need to subtract out the volume of the intersection of those things.
Yes.
Yeah.
Which is long.
Yeah, but not that long. And that's why I've given 2 lines. Hopefully it's enough.
Oh.
So that'll be the volume of x1 plus the volume of x2 minus the volume of x1 intersect x2. Good. Plus the volume of x3. Well, at the very least, I already see volume of x1 plus volume of x2 plus volume of x3. So I'm part of the way to what I want.
Would that plus be a minus?
Which one?
Since we're evaluating this whole thing that would be a subtraction when we do prop 3, then everything would be opposite.
Yeah, so that's I think I've given myself enough space for reordering and maybe distributing a negative sign. So I'll just put do what you want. A negative sign will need to be distributed, but I think we're all comfortable with the idea of distributing negative signs at this point. Volume of x1 cap x3 plus volume of x2 cap x3 minus, which you know will become a plus, volume of x1 intersect x3 intersect x2 intersect x3. Okay, so I didn't give myself enough space, but I kind of did. Well, let's do lots of reordering. Let's distribute the negative sign, and let's do some simplification. x1 intersect x3 intersect x2 intersect x3 is redundant, right?
Yeah.
So I can safely, like, get rid of that x3.
Yeah.
Yeah, let's preserve the color coding. There's the bit that should be underlined in blue, because that's this bit. So let's reorder it. I see volume of x1 plus the volume of x2 plus the volume of x3 from x1, x2, x3 minus the volume of x1 intersect x3 minus, coming from the red bit now, volume of x1 intersect, that's an x2, intersect x3 minus volume of x2 intersect x3 plus, because minus minus becomes plus,
So what do you think? Do you think that it'll be the exact same idea to go from the case of n to the case n plus 1? Yeah. The only thing that would be harder is the bookkeeping. So here's a reasonably straightforward inductive proof. And maybe this is a good example of something. You can only run induction finitely many times. You can't use an inductive argument to get to what happens at infinity. Because no matter how many times you induct, you won't get to infinity.
How?
Unless there's another trick you can do that's called transfinite induction. But I think that's a topic not for this class.
What class would it be for?
Not undergrad.
No, not necessarily. It's kind of set theory, I would say. The idea is there's a property in set theory, the well-ordering principle, which says that if you have any set, there exists a well-ordering on it. And that's equivalent to the axiom of choice. And once you have a well-ordering, that's the setup you need to do induction. Induction says that if you assume something is true for everything before some number, then it should be true for the next thing. And so all you need is to be able to take a next thing. But I'm getting distracted. This is not the topic of today. So we're pretty happy with that argument?
So I think that
Maybe, so here's something that you definitely can't do in just R2. If you're only allowed to take areas of regions in R2, then you have no idea what it should mean to take a product of two regions and what's the volume of that? Because if you take a two-dimensional thing across a two-dimensional thing, that's a four-dimensional thing. So if you want to prove a theorem about what happens when you take the cross product, Cartesian product of two sets, you need arbitrary dimensions. Let's try to prove this theorem, though. Let's try to prove this.
if I give you any two sets, any two figures, x and y, then x cross y is still a figure, and the volume of x cross y is, what do you think the volume of x cross y should be?
Volume of x cross the volume of y.
Yeah, seems reasonable.
So I guess times.
Yeah.
Yes.
No,
I guess you can't take the Cartesian product of number with number.
it's the cross product. Matrices with one element.
Yeah, but a number isn't a matrix, it's just a number.
Unless you're in MATLAB.
Okay. Anyway, it's just
Times.
so
Let's try to prove that. And I mean, that seems somehow reasonable. It agrees with your intuition from like counting. If I take a set containing 5 things and cross it with a set containing 6 things, that new set has 6 times 5 things. So this is the right analog of counting, but for sets that are infinite.
as long as they're sets you can take the volume of. So let's try to prove it. Let's let x and y be figures in some dimension.
If x is in Rm and y is in if
X is in Rn and y is in Rm,
then where does x cross y live?
Rm plus n.
so let's let
R, a subset of R n plus n, be a bounding rectangle for x cross y. And in fact, it's maybe really easy to believe that that R will just be a bounding rectangle for x cross a bounding rectangle for y. That seems believable.
So what do I need to do? I need to take a subdivision of R and try to compute
The corresponding upper and lower volume sums. according to that subdivision. But see, that subdivision,
Well, it's not hard to understand, right? If I get a subdivision of that R, then it's just it's a subdivision of Rx plus a subdivision of Ry.
in the same way as like this picture is a subdivision of R2,
Of a two-dimensional rectangle.
it just comes from taking a subdivision of R1, a subdivision of R1, and putting them together.
And so what do I mean precisely by that? I mean take the Cartesian product of a bunch of elements of delta x and a bunch of elements of delta j. Delta y.
That seem okay so far? And I'm going to try to use that to compute volume. So before I do that, let's try to even decide which things are inner and outer rectangles.
And I guess, well, I cross j, I claim, is an inner rectangle to x cross y if and only if I is inner to x and j is inner to y.
What do you think? Can you come up with a proof for that? Let's try.
And the same thing for outer. I cross j is an outer rectangle for x cross y if and only if I is an outer rectangle for x and j is an outer rectangle for y.
So let's try to do it. And I mean, maybe I'll do like one of them with both of the implications. Inner or outer? Inner? All right.
Well, those of you who would have preferred outer, you're already outvoted. Let's do it. So let's see, if I want to prove an if and only if statement, I guess I need to prove two implications. So let's let I cross j be an inner rectangle for x cross y, comma, delta.
All right. Well, what does it mean to be an inner rectangle? Possibly by flipping back to that front page.
Yeah. What do you mean by in, though? Do you mean is an element of or is a subset of?
Subset.
Good. And I want to show that I is an inner rectangle for x and j is an inner rectangle for y. So what is it that I want to show?
I is contained in X and J is contained in Y.
And if I want to show that, maybe I should start by considering any, I don't know, I and j and j. So let's consider any. I in I and j in j.
All right. Well, let's see. My eventual goal is, I guess, well, I is in x and j is in y. Well, let's try to put together what we know. So I is in I and j is in j. So what can I say about, I don't know, the ordered pair of I comma j?
Isn't it I comma j?
Not comma.
Cross I cross j.
Yes. Then I comma j is in I cross j. But what do I know about I cross j?
Subset of x cross y.
It's a subset of x cross y. So apparently then I comma j is in x cross y. But wait, what does it mean to be in the cross product of two things?
First one's with the first one, second one's with the second one.
Yeah. And j is in y. Oh wait, Thus, I is a subset of X, J is a subset of Y, and finally, I is an element of in of X comma delta X, J is an in of Y comma delta Y. Okay, so I guess I only had enough space to prove one of the implications, but do you believe the other implications are going to be like basically the same symbol pushing? In fact, I think we can prove the converse by like reading this proof backwards. So if you assume those two things, that means I is a subset of X and J is a subset of Y. We need to prove that I cross J is a subset of X cross Y. I bet you can like just rearrange those exact same letters and get what you want. Fair enough. And it'll be something really similar for outer, except instead there will be some non-empty intersections instead of set containers. Moreover, I claim that volumes are multiplicative for rectangles. By that I mean, if I is in delta X and J is in delta Y, then the volume of I cross J is the volume of I times the volume of J. Is that clear? In fact, I think that on the next page, I think I give myself space to explain why. No, but we can. Let's see, if I in general is just going to be some A1, B1 cross dot 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 cross AN, BN. J is some C1, D1 cross dot 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 cross CM, DM. Then I cross J is just the product of all of those things. But we have a formula for volume. If you have then the volume of I cross J, well, that'll be B1 minus A1 times dot 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 times BN minus AN times D1 minus C1 times dot 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 times DM minus CM. But hey, have I explicitly just written down the volume of I times the volume of J in that way? So there's nice. So let's put those two facts together. A product of a thing in the inner rectangle of X cross Y is exactly a product of two inner rectangles. An outer rectangle to X cross Y is exactly a product of two outer rectangles. And volumes of rectangles multiply. I claim that's going to be just everything we need. And let's try to use that. So V minus of X cross Y with respect to a subdivision delta, well, that's the sum of all I cross J's that are inner rectangles to X cross Y. Oh boy, any of those inner rectangles I can write as an inner rectangle for X followed by an inner rectangle for Y. So it's just sum over all inner rectangles for X and all inner rectangles for Y of the volume of I cross J. Well, that's just the volume of I times the volume of J. Everyone with me right now? Do you think I could break that into two separate sums multiplied together? Yeah, you could I guess pull the V of I out of the sum indexed by J because it's a constant in the J's. And then you could pull the sum over all of the J's out of the sum indexed by I's because it's constant in the I's. What you would wind up with the volume, the sum of all of the volumes of I's, where I is an inner rectangle for X, times the sum of the volume of all of the J's, where J is an inner rectangle for Y. Do we already have a name for those two factors? Possibly by flipping back to that front page. What is this sum? Well, it's something having to do with x, right?
Like v minus of something.
V minus of x using the subdivision delta sub x. And this is the same thing but for y instead. Do you think we could have done the same thing for outer rectangles instead of inner and get something else? Similarly, this is the same as v plus of x comma delta x times v plus of y comma delta y.
Nice. So, proposition, well, I claim
It's proposition 1.
says that things are figures if and only if you can find subdivisions for which the inner area and outer area are really, really close. So let's appeal to that.
For any positive number delta, I'm going to say delta here because later on I'll say, well, for a particular choice of epsilon, here's a good choice of delta. So first I'll do it for any positive number delta. X and y are figures, so I can use proposition 1 to find a single subdivision delta x for which 0 is less than v minus of x rel delta x is less than or equal to the actual volume is less than or equal to v plus of x rel delta x is less than or equal to v minus of x rel delta x plus delta.
That's exactly what that proposition says, I hope. And right, the actual volume is always between v minus and v plus, because it's a soup of some things and it's also an inch of some things.
And you can do the same thing for y. You can find another subdivision delta y such that 0 is less than or equal to v minus of y rel delta y is less than or equal to the volume of y, less than or equal to v plus of y rel delta y, less than or equal to v plus, nope, that's a v minus, of y rel delta y plus that small number little delta.
So let's see, all of those, everything in sight is non-negative in both of those inequalities. So I can multiply things together and inequalities are resolved. Right, they get flipped if I accidentally multiply by a minus, but I can't. So if you do that,
you'll wind up with 0 is less than or equal to v minus of x delta x times v minus of y delta y. Oh gosh, I've gotten myself in trouble, haven't I? Is less than or equal to the volume of x times the volume of y is less than or equal to v plus of x rel delta x times v plus of y delta y is less than or equal to, well, the last one maybe I'll write in red because I'm going to do something weird with it. V minus of y delta y plus delta multiplied by v minus of, why did I write the y's first? I guess it doesn't matter.
fair enough. Well, let's look at this. V minus of x delta x times v minus of y delta y. We have that something in terms of x cross y at this point, don't we? That's v minus of x cross y.
And if we set delta to be delta x cross delta y, then there's v minus of x cross y, well, delta, less than or equal to v of x times v of y. It might be really tempting to just like write v of x cross y in that line, but then I would be assuming what I wanted to prove, wouldn't I? Right, I want to prove that v of x times v of y is v of x cross y. So I better not assume what I want to prove. Less than or equal to v plus of x cross y, well, delta, plus that last term. So v minus of, let's see, I'll try to be careful. So I'm going to like FOIL that out.
What do I get when I multiply those false terms together?
V minus x cross y comma delta.
Yeah. Comma, delta. And the remaining terms will all have a little delta next to them. So I'll plus delta times v plus of xul delta x plus v plus of, nope, v minus. Get something like that?
But I mean, now let's consider any epsilon bigger than 0. Can I find a choice of delta so that that quantity is less than epsilon? Wow, I mean, let's just be intuitive. As delta goes to 0, what does this piece tend to? 0. You could actually find a choice of delta that tells you that.
And maybe I'll even just write down what a choice is. Min between 1 and epsilon divided by 2 times the volume, volume of our x plus the volume of our y plus 1. That's a choice that walks, but I don't care about that choice. You can say it's by a limiting argument. Then you can get the right-hand side of this inequality to be less than v minus of x cross y, well, delta. So what does that mean? That means for any for any epsilon bigger than 0, we found a single subdivision so that v minus of x cross y, well, delta is less than or equal to v plus of x cross y, well, delta is less than or equal to v minus of x cross y, well, delta plus epsilon.
But wait, do we have some sort of proposition that tells us that in that circumstance this thing is a figure? Yeah, that's proposition 1, right? So I've used proposition 1 both ways. That's like a common trick that we do. I have a reformulation of what it means to be a figure. I'll just use that reformulation both ways.
So this thing is a figure. Moreover, I have both v of x times v of y and v of x cross y are both between v minus of x cross y, well, delta and v minus of x cross y, well, delta plus epsilon. Do you guys buy that? That we have that? Cool. Well, if I have two different things that are both between blah and blah plus epsilon, the farthest apart that those two things can be is epsilon. So the absolute value of the difference between volume of x cross y and volume of x times the volume of y is less than or equal to epsilon.
And we have that that's true for absolutely every epsilon bigger than 0. And this didn't depend on epsilon. Right, those are just the things we picked in advance. So as a consequence, what can we conclude? The absolute value is actually equal to 0, so they're equal.
So v of x cross y is equal to v of x times v of y, completing the proof.
There was a fair number of moving parts, but hopefully in total the many moving parts made sense together.
Sorry, I can't read what's in the delta. Can you say that?
Yeah, I can say it again. If maybe I'll emphasize that it doesn't matter.
Yeah, I mean, that makes sense. I'm just curious. Delta equals small.
I think one that walks.
Yeah. Number of after 0.
So I'll take the min of 1 and something, so then like that delta can be replaced with 1.
All right.
And then it'll be epsilon over volume of x, well, delta x1. It's certainly less than the volume of the whole rectangle that x is contained in. Same thing with y. And then plus 1 because that last delta is at most 1.
Okay.
So there's a choice that walks. But, I mean, maybe this is like an allusion to how it is that we prove that like the limit of a product of two sequences is the product of the limit of the two. Like it was a single choice of argument that happened there.
Gotcha. I
Nice.
wasn't quite, I thought I was misreading the Rx and the RY notation. Thank you for explaining.
Well, I mean, you probably were because that's totally unreadable. I can't tell what I wrote.
I can't either. I can tell what I read down.
So,
So, naturally, the thing that we want to do with volumes is once we have a sense of volume, you know what I'm going to mean by integration. I'm going to mean like, draw your curve, well, it's not going to be a curve, it's a function from Rn down to R1, then its graph is a subset of Rn plus 1. So just pick all things that have last component less than or equal to that. That's the area under the curve. The definite integral should just be like a model for the volume of that.
and so that's what we'll start in on next time. For now, maybe I'll say that, oh, there are actually two homework problems that I think I've picked out for this lecture. There's this one, and one other which you'll find online. And let's just see what this says. So if you have a function f from x cross r, the graph of f, which I'll denote gamma of f, gamma for graph, is given by just everything that looks like ordered pairs of x comma f of x, where x is an x. And let's even just think about this. I can't draw very many dimensions, but there's like the graph of a function. What would you say the area of the graph of the function should be? Probably 0. And one way that you could try to prove that is like, okay, well, if I cover it with a bunch of little boxes, I can make all the boxes as little as I want by some sort of continuity argument. Maybe I'm assuming that the function is continuous. In fact, maybe I'm even assuming that the function is uniformly continuous. So proposition, suppose that x is a figure, and f from x to r is a uniformly continuous function, then the volume of the graph of f is 0.
So no space filling curve can be uniformly continuous.
That's not quite what this says, because this is only graphs. So, right, so what Jonah is alluding to is there exists a continuous function, f, from 0, 1 onto 0, 1 plus 0, 1, which is continuous, which seems bananas, right? You can't do that. Well, what is, it's like, you come up with it as a limit of something that zigs and zags around a lot. I'm not going to be able to actually successfully draw the thing. And well, each one of those functions is continuous by design. As a map from 0, 1 to 0, 1 cross 0, 1. Notice it's not the graph of a function. It fails the vertical line test like really badly. So it's not the graph of a function. But all of these will be continuous. They'll converge uniformly. What do we know about the uniform limit of a sequence of uniformly continuous functions? Still uniformly continuous. And well, you can also show that the image is like dense in 0, 1 cross 0, 1, but it's a closed set of 0, 1 cross 0, 1. So it has to be everything. But that's getting sidetracked a little bit. And so what this is saying is if you want like to study functions that really behave well under dimension, you need something better than continuity. You need maybe, I don't know, smooth. Because this function is not differentiable. Even like its approximations aren't. They have lots of commas. And in the limit, it's going to be super non-smooth. It's going to be nowhere smooth. Cool. Well, I'll stop there.